Record, okay. Very good. So let's start. So we are already in lecture 4. That's great. This advanced calculus series this year. I mentioned the properties. I listed the properties of cross product, right? So let me recall. So today is just all cross products. Just discuss cross products. So recall the list of properties of cross product that we had last time, right? List of properties of cross product. I'm not going to write all of it. A cross P of two vectors A and B in the three-dimensional space, right? So we had some properties, desired properties that we want them to satisfy, right? So for example, one of them was that this cross product, whatever it is, it has to be orthogonal to both A and B, right? So A cross B has to be orthogonal to A, and A cross B has to be orthogonal to B. And also magnitude of it, we fix the magnitude or we fix the length of this cross product to be magnitude of A, magnitude of B, absolute value of sine of theta. But really, I didn't write it like this. Okay, so I just wrote it as area of the parallelogram based on A and B, right? That's how. So this is area of the parallelogram formed by A and B. And there were some other properties, which I don't talk right now, but the idea was that, okay, we have this vector A and vector B, and we are looking for a vector C, which is orthogonal to both A and B, and its magnitude is area of, okay, it should be this area. This area we know, I mean, from elementary geometry that it's this length times sine of the angle between the two. We can prove that using, for example, the cosine law that we used. But anyhow, it doesn't matter right now. Let's not just think of it as geometrically as area law. Okay. So this is parallelogram formed by A and B, and we look at its area. And its direction also, we had some rules about right-handed rule about the direction. If you go from A to B, this should be in should form a kind of right-handed system and all that, right? Okay, so so the way that it is defined by these by the axioms that you recall from lectures, from last lecture, is that this exists. You know that this vector exists and is actually defined like that. Now, but the beautiful fact is that there is also purely algebraic formula for this vector. So that's really incredible, that there is a purely algebraic formula without knowing all this geometry going through these constructions. You can write down one formula and it will fit the beam, basically. It will satisfy all these conditions. So the formula is this. Let me write it. Okay, so maybe I just write it here then. Let's see if there are comments in the chat. No. So given vectors, A equal to, so let me write its coordinates like A1, A2, A3, and B equal to B1, B2, B3. Define, it's just define the vector A cross B by this rule now, A cross B equal to, it's a determinant, I, J, K, A1, A2, A3, B1, B2, B3. So that's a kind of, I assume you all know determinants, right? You have seen determinants in the algebra. So okay, so that's a kind of, I would say, so we have to understand what is involved here, because it's honestly, we are mixing different things. These are vectors, JKs, and these are numbers. So we are mixing vectors and numbers. But with some understanding, I can just tell you what this really means. This really means this. You just expand the determinant along the first row. So we just, by definition, this is equal to, well, what is this? Just A2B3 minus A3B2 times I minus, then there is A1B3 minus A3B1 times J plus, the third factor, this K is going to be A1B2, A2B1, right? A1B2 minus A2B1 times K. Okay, so this makes sense at least, right? Because these are I, J, K, I3 are these coordinates are unit vectors, and these are just scalars. So this is a vector, right? The result came out as a vector. So this is a vector. Okay, so this is a formal, very mathematical, precise definition of cross product, if you want. Now, if someone gives you this formula, right? Someone tells you, okay, take this, A cross B equal to that. It's very hard to digest what this really means and why this should be useful and what kind of why you don't take any other combinations here to produce a vector. I mean, this looks so, honestly, it looks nice because there is some rule here, there is some pattern, you can see that there's some, but what is the pattern? What is the geometric properties of it? And the point is that this cross product exactly satisfies all those properties that I wrote down. This is a solution to our problem, basically. And to check that is very easy. I mean, for example, checking that this is orthogonal to A and B. Let's check that this vector is orthogonal to A and B. Let's do that, right? So let me just write it down. Check. One, that A is orthogonal to A plus B, and B is also orthogonal to A plus B. How can we do that? Well, so what does that mean? It means that if I take the dot product of A with A cross B, I have to get 0, right? So i.e. A dot product A cross B is equal to B dot product A cross B is equal to 0. So I have a question, very good, in the chat. Okay, so Can you hear me? He says yes. From dot product. Okay, so the question is not addressed to me. Okay, so there seems to be some discussion internally. I'm not part of that, so I'm not addressed. Okay, so I don't know. They were communicating with each other. That's fine. Anyhow, so we have that. So now, why this is the case? Can you tell me how you verify this? This is statement.
Just actually do the dot product?
Just actually do the dot product, right. So, so in other words, instead of I, J, K, we put A1, A2, A3 and multiply, and then we get the dot product, and then we have to get 0. But can you show me an easier way to, so that from properties of determinants, actually this is kind of very obvious by just looking at the definition? A quicker way to do that? I understand this is now this is a bit difficult question, so don't be discouraged if you don't know the answer. From the home audience, do you know how to do this by any chance? Okay, so what does this definition really means in terms of dot product? It just means that if you want to take the dot product, so let me just, so note, so the dot product of A with A cross B is itself a determinant, because what we are doing in the dot product, we are just replacing I, J, K by these 3 components A1, A2, A3. So this is really should be nothing but A1, A2, A3, and then there is A1, A2, A3, B1, B2, B3, right? It just should be this from the definition. All right, so from this now, from this observation, can you tell me why this is 0 then? This is properties of determinants, right? 2 rows are the same, so the determinant is 0. So this is equal to 0 since 2 rows are equal. So you know that in a determinant, if, also there is a question. Yes, R1 is equal to R2, right? So they're already, R1, yes, exactly. C is perpendicular to A, so the dot product of the 2 is 0. Yes, but we wanted to give a proof of that indeed, yeah. But that's essentially correct. R1 equal to R2, yes. Yes, so I have 2 types of solutions. One is algebraic, which is my intention. The other one is geometric. So in the geometric answers, be careful because you are assuming something that we want to prove in your geometric reasoning. So we cannot, I mean, okay, so the algebraic proof, which is the intention here, is anyhow. So this is 0 because R1 is equal to R2. Now, the same kind of token, you see, if I put B here, why this is 0? Well, you have to put B1, B2, B2. So just put B1, B2. Just raise it, and this is B1, B2, B3. And this is B. But then again, this is also 0 because R1 is equal to R3. So there's no questions, but R1 is equal to R3, so determinism. So these orthogonality rules are all kind of symptoms of the way that we have defined it. It follows from the definition easily. And you know a little bit about determinants. So that's good. For example, there was another condition, I mean, another property that a cross product is anti-commutative. It's not commutative. A cross B is equal to minus B cross A, right? So what was, can you tell me how to prove this rule now? A cross B equal to minus B cross A. How do you do this? Anyone knows? Yeah? Proof?
You could show it with the right-hand rule.
Yes, with the right-hand rule, exactly. Or with algebra, how do you approach it algebraically?
Flip the row.
Exactly, we are flipping the last two rows here. So the sign of the determinant will change if you flip the rows, right? R2 exchange with R3 sign change in determinant, right? This is what you know from your linear algebra or from some calculus classes you're taking. So, I mean, you can take a kind of, maybe this is a bit of a highbrow approach. You can take a kind of quite down-to-earth, dirty approach. Just sub in and do the calculations, and you notice that you get minus some. But then I bet the chances are you're going to make mistakes because these calculations are so long. So you will lose track at one stage. I will lose track at one stage, and then I'll make mistakes. So it's better to have some sort of conceptual understanding of these things always, instead of sometimes computations are unavoidable anyhow, so we have to do that. But here is okay. So one formula I want to drive again along this line is that what if you take the dot product of any vector with this cross product? So I'm going to write it like this now. So if C is any vector, of course, so in general then, for any vector C, or any third vector, I would say, C, we have C dot A cross B is equal to determinant of, well, you just replace ijk by C1, C2, C3 because the rules are set. So this is C1, C2, C3, A1, A2, A3, B1, B2, B3. So this is a very valuable, very, very useful formula. This formula is extremely useful. So, and we just derived it almost without any effort. Okay, so I can erase this. Now, we can use any questions, by the way, so far? Any questions? No? Okay, so now some applications of this construction that we want to see is to solving some geometric problems. For example, using cross product to find areas of triangles, for example. So let me give you an example of this. Because, you know, the magnitude of cross product gives an area of the parallelogram, so it's conceivable that we can use the formula to compute the area of the triangle by halving it, right? Okay, so now let me just give you an example. So imagine you have some sort of cube. Okay, and you are interested in computing the area of the triangle that has vertices O, say P, Q. So you just draw this. So you can imagine there is a plane that cuts inside, and this is. So we want to know the area of the triangle formed, or I mean, I would say with vertices at O, P, and Q on a cube. So I'm assuming the length of the cube is A. I mean, okay, so maybe L. Right? Let's assume the length of the cube is L. So how would you approach this question? How would you do this problem? If you didn't know about cross product of or these formulas, there would be a kind of sure bet approach, right? So we would just find this length, for example, and then we have to find the height of this triangle, and then multiply height by base divided by 2, right? But that would be a bit difficult because going through that is kind of, it's rather lengthy and difficult. However, we know that the area is exactly equal to using this cross product. So from cross product definition, so if you take this vector OP, for example, and cross it with, well, this is OP, and cross it with OQ, right? Cross it with OQ. So what is the length of this cross product? You think it is? How much is the length of this cross product? What is the magnitude of this cross product? We know what the magnitude of cross product is, right? It's the area of the parallelogram formed by these two things, right? So imagine this is like OP, and this is OQ, and we have got that, right? So, okay, but we are interested in really half of this, right? This area. So area of triangle is half of area of parallelogram, right? So area of triangle equal to half of area of this equal to half of, well, this determinant. Can you see? Equal to half of determinant of, half of, I mean, not determinant yet, this. Okay, all we have to do then is to find this area of that triangle, which is like there, is to compute a cross product. Now, what is this vector OQ now? What is this vector OQ? Okay, so we have to make some choices. I mean, this is a cube, right? This cube has nothing to do with coordinates or anything. It's just some cube in the space. Now we are going to put it on the basis coordinate system. So O is at the origin. This is like, imagine this is the x-axis. This is your y-axis. And this is your z-axis or z-axis. Okay. So this is x, y, z. So with this convention, can you tell me what is the coordinates of Q, for example? What is the Q coordinate? I mean, OQ vector. What kind of vector is that?
Lx plus 0.
Exactly. Yeah. So this coordinate is first coordinate is L. The second coordinate, y coordinate, is 0. And the third coordinate again is L. So this is L. No question from me. Okay. So now what about the vector OP? Okay, so the vector OP is in Y or Z plane, right? So it has an L coordinate here, and it has an L coordinate there, but its X coordinate is 0 because it is in this. Okay, very good. So I have to take a cross product of these two vectors now. So let's do that. So OQ cross OP is equal to this determinant I, J, okay? Now I just put OQ, sorry, this is L0 is L. And then the second one is 0 LL. Okay. So this is equal to now. So when we do this, this is 0, this is L2, right? This is L2 times I minus whatever this, what is this coordinate? Again, this is L2 times J plus last coordinate is L2 again. Okay, so we have got our vector. That's nice. Now, what we should do next? We should find its length. So, what is the magnitude or norm or length of this vector? OQ plus OP is equal to square root of. Okay, let me check again. We have done everything right. It seems we have done everything right. Yes. So, can you tell me the how you calculate the magnitude of this vector now? There are no questions. Yes. What is the magnitude of this? Well, you have to square this, add them, and then take a square root at the end. So this is L4 plus L4 plus L4. So that's, well, obviously it's L2 root 3. Right? That's L2 root 3. So what is the area of the triangle then? It's half of that. So area of the triangle half of L2 root 3. Yes. Yeah, because the magnitude of cross product is not the area of the triangle. It's what?
Oh, sorry. Shouldn't the like the L squared I, shouldn't that be negative L squared I?
Okay. Yes. Yeah, absolutely. Thank you. Thank you. Yes. Very good. It should be minus L squared. Okay, so that's correct. But the final result is the same because plus minus squared is the same thing. So that's good. So we have that. Okay, so that's the final answer. So that's one application of this cross product. So you can solve a lot of difficult geometric problems using cross product and dot product combined together. It captures a lot of geometry of three-dimensional space. So that's pretty good. 1/2 the magnitude. I have very good questions. Actually, I've been getting comments, but since my chat was open, I didn't notice. So that's so I have to close the chat every time so that I get red signals. Well, thank you. Yes, your answers are all correct. Very good. Okay, so I'll just close so that I get signal next time. Okay, so we can compute these areas. Another application is, yeah, so let's see, let me ask you a question now. This cross product is actually so this is maximized when you think this, if you have two vectors and the only thing that you can fiddle with is the angle between the two, for example. So how can you maximize this quantity, the magnitude of cross product? Yeah.
When they're perpendicular.
When they are perpendicular, right? Is maximized if A is perpendicular to B. I mean, do you know how to prove this? Because it's just length of A, length of B, sine of theta. Sine is maximized if and only if theta is maximized. So you know how to do that. That's very good. And is minimized actually equal to 0. So this is really the minimum possible because it's a non-negative number, right? So it's a minimum. If they are what? Sorry?
Parallel?
They're parallel, right, on the same line, they're parallel, exactly. If A is parallel to B, so this is parallel. Very good. Now you should compare these two with the corresponding rules with dot product. The dot product A dot B, absolute value, is maximized if, can you tell me that this guy is maximized? If they are parallel, that's the opposite. If A is parallel to B, and equal to really 0, of course, if and only if A is orthogonal. So in some sense, it goes in the other direction compared to cross product. But there's a big difference between cross product and dot product. Can you tell me what is the conceptual difference between the two, really? Yes.
So cross product gives you a vector.
Yeah, exactly. So there's a big difference. Cross product is a vector, but dot product is a number, is a scalar. So they are very, very different. So we have to be aware of that. So that's very good. So now, one thing that I still want to do is the volume of a kind of parallel pipe formed from three vectors. And there is a triple scalar product. So let me just erase this down. Looks like there are no questions. Okay, so this is triple scalar product. Is it called triple scalar product? I'm not sure what it's called. Well, I don't know. That's okay. Triple scalar product, I call it. And volumes of parallel pipes. So the problem is this. So we have got, okay, so now three vectors, A, B, and C. So these three vectors need not be orthogonal, okay? So that's not a kind of cube or rectangular thing or box or anything. So need not be orthogonal. And so you can go and construct a parallel pipe based on these three. So you get now you can construct some shape like this. So this is your A now, this is B, and this is C. Okay, and the question is, what is this volume? So volume of this is equal to what? So we want to know the volume of this parallel pipe. So how can we compute the volume? Well, the volume, we know what it is geometrically, right? The volume is going to be, you have to draw this line orthogonal to the plane, right? Say C, I don't know, maybe P. And then you multiply this height by the area of the base, right? So volume is equal to height cross area of the base. So area of the base, we know what it is, right? It's just cross product of A and B in magnitude, right? So this is A cross B magnitude. Now, what is this height? Well, the height is going to be, so if you just do this, so this is this height. So this is this length times cosine of this angle, right? This is height. Can you see?
Yeah.
Okay, very good. So h is equal to magnitude of c times cosine of theta. Okay, so what we have to do then is the following. So the following formula we draw. So then we get that volume is equal to norm of C, norm of A cross B times cosine of theta. Right? So, but where is this vector A cross B? Vector A cross B is orthogonal to both A and B, so it's definitely along this line, right? Somewhere, this is A cross B. Right? So this theta then is the angle between A cross B and C. Right? So theta, so I just say note from this geometry of the pictures that theta is the angle between A cross B and C. So this is another extra piece of information I need in order to proceed. Right? Okay, so we have all these things together. So what can you then confer from this information that we have produced here? Now, volume is norm of C, norm of A cross B times cosine of theta. And I'm telling you that we discovered that theta is the angle between A cross B and C. So what kind of vector you can perhaps suggest that this would be its magnitude? Sorry?
The scalar product.
Scalar product. It would be. It's going to be a dot product. Exactly. So the conclusion should be that, indeed, that volume is equal to length of the scalar product of C with A cross B. Very good. So this number we computed before. So this is, I just say, but C dot A cross B is equal to what? We discovered that this can be written as, you have a question?
No.
Okay, so this is equal to this determinant C1, C2, C3, A1, A2, A3, B1, B2, B3. So, and this is called the triple scalar product. This is this triple scalar product. Okay, so we found the formula for volume now. To do the volume, you have to compute the determinant, that's all. To compute the volume of a parallel pipe formed from vectors A, B, C, all you have to do, put them into a determinant, 3 by 3 determinant, compute the determinant, and take its absolute value. I made a mistake, kind of conceptual notational mistake somewhere. Can you tell me where I made a mistake? Notational wise, I have transgressed from the standard notation a bit. Yes.
You took the norm of the scalar product?
Exactly. I mean, norm should be reserved for vectors, but this dot product is a number, right? So I better don't put this, right? So because this is a number, and so without absolute value signs is just this concept of triple scalar product, and with absolute value, if you take its absolute value, then you get really the volume. So the volume is not really triple scalar product. Volume is absolute value of the triple scalar product. So I have a question in the chat, or maybe a comment. Volume equal to C dot A cross B, not the magnitude of that. Oh, there is a suggestion that the volume is equal to C, not the magnitude. The volumes that we are taking cannot be negative, right? So you have to take the magnitude of that. And C dot A cross B is not a vector, by the way, is a number. So when you say magnitude, perhaps you mean absolute value, right? Did you get my comment? Okay, very good. Yes, excellent. Yes, question.
Why is it called the triple scalar product for only taking one scalar product?
Yeah, I'm not sure. You see, I struggle to remember the exact terminology. Maybe you can tell me the exact terminology. I don't know. I have taught this only last year, so, so I don't. But what's the right terminology now that you ask?
That's what we learned in high school.
Oh, it's called triple scalar product, I think in your book also. So yeah, that's a fair question. I mean, yeah, I also thought about this issue. But, yeah. Okay, so any other questions? Or so volume is really, I mean, this formula. Now that you have the formula, you can say something. This quantity is very interesting on its own, whether it's absolute value, is volume or not. So let us write this, for example. So now, for example, if you exchange this with that, you get a negative sign, right? So determinant of B1, B2, B3. Now we have A1, A2, A3, C1, C2, C3 is equal to negative determinant of the original one, which is C1, C2, C3, A1, A2, A3, B1, B2, B3, right? So from here, you convert that to B dot A cross C is equal to negative C dot A cross B. So this is cool, right? I mean, if we have to think about it like this. It's not clear why this should be true, because that's a kind of strange rule. I mean, but it follows from properties of determinants. You can so what is the rule of moving these things? So, for example, what is C? Well, C I have done. So maybe A we haven't done. What is A dot C cross A, for example? What is the relation between this A dot C cross A and C dot A cross B, for example? This is this one. And for here, we want to put A in, so I'm going to start it like this. I'm going to put A in the first row, C and A here. Oh, no. B, I meant B, sorry. C and, C and B. But this one is C, A, B. So these are rows, of course. So what's the relation between these two determinants? These two determinants. It's negative, exactly. It's equal to negative of that. So the rule is this. But not always. If you, for example, bring this down, so I would say B, C, A. So it shows that A dot C cross B is equal to B dot A cross C. You can play with these things and discover new identities, which just follow from determinant if you have this in mind, but just thinking about it. Now, can you tell me what is the meaning of this in terms of volumes? Meaning of these relations in terms of volumes, for example. So I have a question, okay. Equal, yes. Oh, there was a minus sign though, right? Okay, never mind. Yeah, okay, that's fine. Yeah. So, can you tell me what is the meaning of these relations in terms of volumes? Volumes of parallel pipes. You see, these numbers can change at most with the minus sign, so the absolute values are the same, right? So what does it mean? It means that if you want to compute a volume, actually, that it tells us something very natural. If you want to compute a volume of a parallel pipe like this, oh, this is coming out like a angular box, but forget it. Imagine it's a parallel pipe slanted, very generalized. Okay, so you can do different things. You can take this as your base, multiply this height as projected from here to this, or you can take this as your base, or you can take this as your base. And the height is going to be different. So you have three different formulas for the volume, and they're all the same. So this is incredible if you think about it. I mean, if geometrically, if you see this, it's hard to believe that this should be true, actually. Sorry. It's really hard to believe this should be true. I mean, let me give you a simple two-dimensional version of this. Maybe you think about it. So imagine you have a triangle. So I'm saying if you multiply this by that, is the same if you multiply this by that, is the same if you multiply this by that. But why it should be true? It's completely weird that such a thing should be true. I thought he changed two rows. Yes, remains the same because it's absolute. Yes, volumes remain the same. Yes, exactly. Okay, so, you know, some statements in terms of algebra are very transparent. In terms of geometry are not transparent at all. They look very, very mysterious. And there's also the other way around. Sometimes the statements in geometry are very transparent. If you write it as equations, algebraic equations, they are very, very mysterious. So the thing is two ways. It's not that algebra is superior to geometry or geometry is superior to algebra. They are more or less on the same footing, although I think geometry is superior to algebra. That's my point of view, but some other people don't accept. Right? So you can have your own point of view. So there's a fight between geometry and algebra all the time. So it's going on all the time. So they have the schools of thought, but the main thing is that they are really collaborating with each other to get something more interesting. So doesn't matter. So let me just answer this question. So doesn't matter B crosses, see when calculate. That's right, exactly. It doesn't matter because you have to calculate the absolute value of that number for the volume, not the triple cross product itself, the absolute value of the triple cross product. That's my convention anyhow. Okay, guys, so thank you so much. It was great to have you here. Also, the audience at home, that's great to have you there. And I see you on Friday. And send me emails if you have questions or whatever. Thank you. Thanks. So.